So this is for lesson C, and lesson C is for C and D in your textbook. So D is going to take like 3 lessons probably, so this is for C and D. So now what we're going to do, now that we know we have distributions, is we're going to describe those distributions. So what do they look like? So when we describe these distributions in AP Stats, we're going to use this acronym called SOX. And what that stands for is the S is for shape, the O is for outliers, the C is for the center, and this last S is for the spread. Now, a lot of times, and even in AP Stats, you'll see this another way too, and it's SCVU. And so we're talking about the same things here, but I don't know, it's just a different way that they can say this. So the first one stays the same, that's also still shape, okay? And then center is also the same, center. And this V is for variability. And variability is the same as your spread. So your spread can be what's happening, so this is usually from the least value to the greatest value. So we can look at it as variability, or we can look at it as spread, same thing. So these two kind of go together. And then for outliers, this is called unusual features. Now, an unusual feature can be an outlier, but it also can be a gap in the data or clusters in the data. And so when you see outlier up here, you're going to hear me say SOX more than this one because I really don't have an acronym for that. Think outlier is also going to include gaps and clusters, and it'll make more sense like once you kind of see how this whole thing is. Okay? All right, so here's what we have. So after we have a graph of quantitative data, we want to describe the pattern, and then from the pattern, then we're going to have to answer questions. And these answer questions from the data is going to be our justify. So when it says justify, we've got to know what the pattern looks like so we can justify. Okay, now we don't use this acronym to describe categorical variables. And so the reason for that is very simple, that when we have a category, or categorical variables can go, can go in any order. So if they can go in any order, then the shape doesn't make sense. And what you're going to see here is that we're going to line everything up and we're going to put everything in order based on our discrete or our continuous variables. Okay, so categories will be placed in any order on the x-axis, so shape wouldn't make sense, so that's basically what I said up here. The same thing for center and spread. We can't find the center of a zip code or the average of a zip code. All right, so we can see how many zip codes we have, and that would be a quantitative variable, but the zip code itself, that wouldn't give us any information. All right, so first thing that we're going to talk about is shape. And shape's going to be really important when we look at how we're going to analyze data. So we've got all this new vocabulary in here. We're going to talk a lot about this over the next week or so. But the first thing that we have is something that's called unimodal. And the easiest way to talk about this is I have one hump in the data. Okay, so it might look, if I have something like a histogram, it might look something like this, right? So I have this one hump and it's happening right here. Okay, but it doesn't have to be in the front either. It could be something that looks like this if I'm looking at a histogram. Okay, so here's another histogram, and this would be my one hump. It's the tall part that I have somewhere in there. So it does not have to be, so I'm going to put that, doesn't have to be in the center. Okay, all right, so the next one we have is bimodal. So hopefully you can guess with bimodal, this is going to be 2 humps. Okay, so I can do something, if I do a histogram again, I might have something that looks like this. Okay, so what I see is that I have 2 tall data points. Now, it doesn't have to be in a histogram. So let's just say, for example, I have a stem plot, and I have 1, 2, 3, 4, and I have 2, 3, 2, 3, 4, 5, 2, 3, 2, 3, 4, 5. So same thing here. So I have 2 humps on here. So if I look at it sideways, you can see how this distribution would look similar to this distribution. Okay? If we have something that's uniform, hopefully you see that these are all the same height. And this can be H-E-I-G-H-T. All the same height. And it doesn't have to be the same thing. So for example, it could look like this. If I had a histogram, it could look like this. And you're like, well, wait a minute, those aren't all the same height. Well, look at this histogram, right? And then look at this one. So this is significantly different. So this goes all the way down, or I have this big hump where I go up, down. This, if you think about it, is all pretty close to being the same. So this would all be about the same height. It could look like something like this on a dot plot. I could have this. So this would be pretty uniform. I don't have anything that's sticking way up. So just as example here on a dot plot, if I had something that would be bimodal, it would look more like this. So I would have 2 distinct humps, whereas this is just pretty much the same all the way across. Okay? All right, so next thing that we have is something that is symmetric. So if I have something that's symmetric, then symmetry means I'm going to have a mirror image. And this is not going to be exactly 100%, but it needs to look pretty close. So for example, let's just say I had something that looked like this. And if I break this down here in the middle, this side and this side are pretty close to each other. We would also say in this one that this is unimodal. So I have this one hump that's happening right here in the middle, so I would say that this is unimodal and symmetric. Okay? I could also have something that looked like this. I'll do it with histograms again. If I have something that looks like this, okay? So if I draw my line down the center here, I would say that this is symmetric, 2 M's, and it is bimodal. Right? So I have this hump that happens here, and I have another one that happens here. Okay? Now, one of the most common things that we're going to do is talk about data that is skewed left or skewed right. So what happens when I have data that is skewed left is it's going to look something like this. Now, what this means is that we have a tail to the left. And one of the ways that I saw this one time, if you think about this, this is what the data looks like. If you think about, you've got this skier right here, and he's skiing and he's going down the hill. He's going down the hill to the left. So that just kind of always stuck in my mind. But what happens is if this is skewed left, we're going this direction, and the tail, so left is where the tail is, and this is my cluster of data. So the cluster here would be on the right. Okay, so obviously if that is skewed left, then if I had something that looked like this, and I have data that's clear over here in a histogram, this would be my data that would be skewed right. So I'm going this direction, so here I have the tail on the right. Okay? All right, so let's flip that over. If I want to draw a symmetric bimodal distribution, oh, I just did one of those. If I did a symmetric bimodal distribution, I would have something that looks like this. So I have a hump here, I have a hump here. It tells me I have 2 of them. It's symmetric down the front, so it would look something like this. If I want to draw a unimodal, so unimodal is going to be 1 hump, and it's right skewed, so this tells me that the tail goes right. Then I'm going to have something that's going to look like this. That's going to be my data. Okay? All right, so based on what we just did with all of these different things up here, so shape, center, variability, unusual features. I've got a problem here, and we're just going to work through talking about what all of these different features are. So it says tropical cyclones are severe rotating storms that originate in tropical oceans. One measure of severity of the tropical cyclone is maximum sustained wind speed, which is used to classify the storms as tropical depressions or tropical storms, hurricanes, or major hurricanes. Okay, so I have this dot plot of the winds sustained for 193 tropical cyclones in the Atlantic. Okay, so I want to describe the distribution. This is my question. Okay, so if I look at this, if I go up here, and I'm going to start with my shape. So if I look at my shape of this, what's happening is this is definitely skewed right. I have a tail that's going off in this direction. I also have one major point right here. So I am going to write this, and what's really important, in fact, I'm going to make a note here. So we have to use the context of the example or the problem. So my shape here, I'm going to say the distribution of wind speed for 193 cyclones is unimodal and skewed right with a peak, that's what makes it unimodal, right? With a peak at, let's see, what's this at? Maybe 45 knots. Okay? All right, so this is what I would say for my distribution. Go ahead and pause the video if you need more time to write this down. Okay, so the next thing in my description would be O. Remember, we're using the acronym SOCS. So to describe the distribution, this is what I'm going to do. So this is going to be outliers. So outliers or unusual features. So an outlier would be something that would be hanging out clear out here all by itself, or something that's hanging out over here all by itself, but there's no gaps in my data. So this is definitely skewed right, but I don't see big gaps in my data. So I'm going to say here that there are no visible outliers. All right, so next is center. So the center is, where is the center of this data? So I can look at it as the center of the data is right here in the middle, but when we look at center, and we're going to do more of this here in just a second, we're looking for mean, median, or mode. Okay, so the middle of my data, if I look, these are all single storms, and they have all of these big storms right here. So I'm going to say that the middle or center of the data is approximately, and we're going to calculate this directly here in a little bit, but right now I'm just going to say it's approximately, I'm going to say, I don't know, like right in here somewhere probably, so 55 knots. Okay, and then the last one, SOCS, S is my spread, and I'm going to say here that the max wind speed varies from, what is this, probably 25 to 160 knots. So, important thing, context of the example. I talk about wind speed, I talk about the units. Make sure you have your units on here. Units came from the graph. Okay? So this is just a super general one. We're going to get into some more specifics now. Okay? So 3 measures of tendency. You've seen this ever since you were in early elementary school, and these are going to be mean, median, and mode. Okay, so we're going to focus on the mean, and the mean is the average. We're never going to call it an average in stats. It's always going to be the mean. And now we're going to do this kind of a little bit funky way that you haven't seen before. So we know that what the mean really is that we're going to add all values, and then divide. So we're going to add them all up. We're going to divide by the total number. But we have some new nomenclature here that we're going to use. So when I have a mean, the mean is now going to be written as an x with a bar over the top. So we actually say x bar. And that's what the mean is. So whenever you see this x bar, we know that this is going to be a mean. And my formula for that is going to be the sum, that's what the sigma is, of all of the x values divided by the total number of values that we have. Okay? So sometimes you don't see this I. Sometimes you'll see that the x bar is the sum of all the x's divided by the n. Now, if you are in AP Calc right now, you might see it this way. So the sum from x equals I to a number of x over n. Now, we will not use this way. So this is what they use in AP Calc. They use this summation that looks like this, but we won't use it that way in AP Stats. We're going to use it this way right here. So I'm going to highlight this because this is super important. This is our formula. It looks fancy, but really all you're doing is you're adding them up and dividing. So what do the variables be? Mean of the sample is our x bar variable. Each individual observation is x sub I. So we would have first observation plus second observation plus third observation. So we would write it like this. The number of observations is n, so that's what we would divide by. And this capital sigma just means we're going to add them up. So we're going to add up all the individual ones and we're going to divide by the total. That's all it means. Okay, so we have this exam right here. It says the reason we don't always use a mean to describe the center has to do with outliers. So we're going to calculate the mean and we're going to talk about outliers. So if I look at this, I have 1, 2, 3, 4, 5, 6, 7 tests. And so if I want to calculate the mean of those 7 tests, then I'm going to add them all up and I'm going to divide by 7. So go ahead and do that and then come back. Unpause the video. Okay, so here's what I came up with, 78.286. So let's go back over here. This says there's clearly an outlier, and the outlier is this 0 score. So, I mean, this guy's cooking. He's doing pretty good, and then he gets a 0. So why might there be a legitimate reason that he has a 0? So maybe he was absent. I don't know. That's what I would think. Maybe he needs more time. So more time to finish a test. And so it's kind of gone in there as a placeholder. So anything like that would be a legitimate reason for why we might actually have a 0 there. If you look at the next page, it says if we cannot eliminate the outlier, we would calculate the mean to be, and we just did that, 78.286. So this is what my mean would be. But if we did eliminate the outlier, so let's do that again right now. So we have the same amount of numbers, but this time I'm going to divide by 6. So if I take that number and I divide by 6, now I get 91.333. Now, if you look at our guy over here, he's pretty smart. I mean, these test scores are pretty good. So it makes a whole lot more sense that his average or his mean is 91.3 and not 78.2. That 1 0 brought him down to a C, where the rest of the time he's got a 91 test average. So what is the outlier doing to the mean? So it brings down the mean. Now, in this particular case, if you look at the data points, this data point here was a 0. But let's say that they got extra credit on a test or they did something, and let's say that that score was a 200. Well, a 200 would totally skew this data, and it would go the other direction. And so we can't say that it's always going to bring it down. This one's going to bring it down because we're adding a 0 in there. But if I added a 200 in there, that would take it up. So you have to look at the context of the problem, okay? So what happens, this is an important term here, is the mean is called non-resistant. And what this means is that it is strongly influenced by extreme values. And our extreme values are usually those outliers. If I was to graph this on a dot plot, I would have this 0 here, and then everything else, so 86, 88, 90, 92, so all of the rest of my data would be up here. So I've got this huge gap in my data that gives me this outlier. And that's what this is saying, that the mean is called non-resistant, because when you have an extreme value, it changes. And so we call it non-resistant. It doesn't, it's not as reliable because it's not going to be in the center anymore, okay? So we need something that's going to take those outliers and not have it affect the data so much. Like up here, it affected the data significantly. So what we have is, if we want to find something that's resistant to outliers, it's not going to change significantly, that is going to be the median. And the median is the middle value. So if we want something that's resistant, so this means that we're going to have an outlier, then we want to use the median. So we're going to look at the data, we're going to determine whether we use the mean or the median. Okay, so let's look at this. It says, the table below shows the salary of 12 employees in a company. So I've got this data right here, and it says, find the mean salary. So go ahead and pause the video and go ahead and calculate the mean. All right, so we've got 12 data points. If I add all these up, I got 601 divided by 12, I get 50.083. So what does this mean? So if these are the salaries, and this says that this is in thousands of dollars, that means that the mean salary, which is X bar, is going to be 50,100 approximately, right? If I round this up. So that is what the average salary is per employee, okay? But if we look at the salary, we see we've got this huge outlier. Maybe he's a COO or some bigwig at the company, right? So let's look at that, because we just said up here that if we have an outlier, then the mean is not the right way to calculate it, okay? So if we look down here, so these are already put in order. So when we're looking at the median, we have to put them in order. And when we do this, I'm gonna show you the old school way to do this. So we go get rid of the ones on the outside, and then we move in, and we move in, and we move in, and then these two are left in the middle. And since those two are left in the middle, we're gonna take and we're gonna add them up, and we're gonna divide by 2. And this tells us 34.5 is in the middle. Now, you can look at this and you can say, okay, what's between 34 and 35? It's 34.5. So you don't really have to do the math. You would do the math if this was some bigger spread. So what this means is that, that the median salary, oh my goodness, I don't even know how to spell salary. The median salary is 34,500. Okay, so here's your takeaway. So we need something that's resistant, because the salary of 185,000 significantly impacts our middle or our center tendency. Okay? So big difference between 50,000 a year and 34,000 a year. Okay, so there's a quick way for us to calculate this. So we have this formula that we're going to use, which is n plus 1 divided by 2. Now, if I look back over here, if I count up these data points, I know I have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 data points. So what we're going to do is, if we have something that's even, we're going to add up those data points. So in this case, it's going to be 12 plus 1. And then I'm going to divide by 2. So this would be 13 divided by 2. And this divided by 2 is just so that I can get the average. And if I look at this, this is the same as 6.5. So 6.5 means that I'm going to find the value between 6 and 7. Okay, so what this looks like graphically is if I have 4 data points, 1, 2, 3, 4, and I look at this, I have 4 data points, right? Up here I had 12 data points, plus 1 is 5, and 5 divided by 2 is the same as 2.5. So I'm going to find the value between 2 and 3. So here I would find the value between 6 and 7. So if I go back over here, 1, 2, 3, 4, 5, 6, and 7. So these are the 2 data points where I'm going to find the value. So I don't have to go from the left and from the right and move all the way in. I can do it from the math. Okay. Same thing if I have an odd number. Odd number is even easier. So 2, 3, 4, 5. If I have 5 data points, I'm going to do the same thing. So 5 data points plus 1 divided by 2. This means I'm going to pick the 3rd value. And if you look at this, 1, 2, 3, that's what's in the middle. Okay, this works every time, and that way you're not counting. As we get into bigger things here, you'll see. Okay, so I have a question here. So the boss is trying to hire you to work at the company, and she says, our typical salary is $50,100. Is this misleading? Why or why not? Well, you can look at the data, and you can see that it's absolutely misleading because we have this one outlier that is driving up that average. Okay? All right, so let's look at this from a histogram. So I have a histogram, and it says the graph below shows the ACT scores among a group of students. Approximate the median ACT. So if I do this, the first thing I have to do is I have to count each frequency. And this is going to be my n value. So if I look at this, this is 2 data points, and this is 3 data points, and this is where I'm coming from. So between 9 and 12, the height of this histogram is 2. And between 12 and 15, the height of this bar is 3. This bar looks like 5. This bar looks like 7. I'm going to say 9, 9, that's 8. 7, and 5. Okay, so I'm going to add all these up. So if I plug these in my calculator real quick, I get 55. So n equals 55 data points. There were 55 students that took the ACT. Okay, and I want to find the median. Well, if I use my formula of 55 plus 1 divided by 2, this is 56 divided by 2, which is 28. Now, what this means is the 28th term is the median. Okay, so here's how I do this. So my first I have here is 2, and I add 3, so this becomes 5. So I got rid of these. And now I have 5 plus 5, which is this guy, so that's 10. And then 10 plus 7, so this is 17. And then I have 17 plus 9, which is 26. And then I have 26 plus 9, which is going to be over my 28th term. So that means that this bar right there, somewhere within 24 and 27, is where my median comes in. So here's what's a little bit tricky. So the median is going to be 24, between 24 and 27. It's this bar. So if you remember, the lower limit has the equal sign. So this means it can equal 24 and go up to 27, but not including 27. So my median here is a range of numbers and not a single value. And that's what you get when you get a histogram. It's different when you have something like a dot plot. Okay? All right, so the next thing here that's very wordy, but basically what this is saying here is that we could also be looking at things in terms of mode. And to be honest, I really don't even know when you're going to look at mode. Okay, so if I look at just mean and median, though, we can tell a lot from this. So if I look at this data right here, I know right away that I have this 0 outlier. We already did this up above, and we know that our two numbers are very different, okay? So here's the two notes. These are the two takeaways right here. So this is not always saying that median is better, but when there are extreme values or outliers, median is the better measure of center. And median doesn't have a special thing, so if you remember mean, we write this as X bar. For median, we just use MED. Even your calculator is going to use MED. Okay? All right. I'm going to go ahead and skip this part right here. All we're doing is finding mean, median, and mode. Well, actually, maybe I shouldn't. You know what? That's what I'm going to do. Go ahead and pause the video, and you calculate mean, median, and mode on these. They're already in order, and then we'll come back, and I'll help you with these histograms and creating the shape. So go ahead and pause it and find your mean, median, and mode just to practice. Okay, so here are my data. So now I'm going to actually create this histogram over here, and I'm going to break this into, let me do, this is 70, 80, 90, 100. Okay, so if I look at this, and then I'm going to go, my counts will be on this one, so this one is my frequency, and this one is my score, or my grade. Okay, so I have two here that are in the 70 to 80. Remember, if it's included 80, it's on the lower level, so I have three that are here, between 80 and 90, and I have 1, 2 that are over here. So it's going to look like this. Okay, do the same thing over here. 70, 80, 90, 100. This one, actually, I have to go to 110, and I'll show you why here in a second. So I have 1, 2, 3, 4 here. So this bar is going to go here. I have 185, so I have one that's going to go right here. I have nothing between 90 and 100. Because this is 100, this is going to be my lower limit. So it has to go here from 100 to 110. All right, and then let me do this last one. So 70, 80, 90, 100, and I have two 70s, two 80s, and three 90s. Okay, so here's what we have. So if we have these different graphs, I'm going to talk about the shape now. So this is unimodal, and it is symmetric. So I'm going to say unimodal and symmetric. This one, I have this going on here. So this is going to be a right skew, or you can say skewed to the right. Okay, this goes the opposite direction, right? This is going down this direction. So this is going to be a left skew. Okay, now I'm going to talk about something here, and I'll just use this middle one for an example. If you were going to write this on the AP test, these would not give you full credit. Okay, that's what it is, but this is how you're going to get full credit. So put on here AP exam. And we'll do a lot of practice when we get closer to the test. But the way we have to write this is the distribution of test scores. I'm going to go say for the 6 tests is skewed to the right, or right skewed. Okay, so what you have to have here is you have to have context. You have to say what is skewed. Okay, so now, because we talked about mean, median, and mode, we are going to do something here that shows you unimodal symmetric, left skewed, right skewed. So the same thing that we have up here, and I'm going to draw these where they look more like this. Then I'm going to have something, if it's left skewed, it's going to look like this. I should have actually done these differently, I guess, now that I think about it. If it's right skewed, it's going to look like this. All right, so here's my data for these. And what this means is if it is unimodal and symmetric, I have this. And when I have something like that, the mean is going to be very similar to the median. When I have something that looks like this is my extreme values down here. So if you remember what we did earlier, if we had an extreme value, then that is going to lower our mean. So what we end up with is that the mean tends to be here, and then the median tends to be here. Think back on that test score. When we took that 0 test score out, what that did. So when we put it in, it lowers our mean. Here is where my extreme values are for this guy. So that means that my median is going to be here. But now I'm going to have this false sense that's up here, and this is going to be more of where my mean is. Think about the salary. The guy that had the high salary, he raised our mean, and the median is really clear back here. Okay, so this is really what this looks like as we think about whether we're using mean or median. So this will kind of give you an idea of what's going to be a better center of to use. Okay, so outliers. Let's talk about outliers here for a second. So an outlier we talked about is an individual piece of data that doesn't fit the overall pattern of distribution. So an outlier is just something that is hanging out. And the important thing about an outlier, especially when we get into graphing this on the calculator, is when the outlier occurs, we have to know why. So a lot of times, the majority of the time, it happens because of a mistake. So maybe you put the data in wrong, or you plotted it wrong. If you put it in your calculator incorrectly, you can end up with a outlier. So that is one of the reasons why we always plot our data first, because we want to see, do we have some extreme value out here that's going to mess up our data? If you do have an outlier, then we have to know, okay, sometimes we really do, like with our salary guy. If that happens, we need to know, we just have to justify it. We have to write what our outlier is. So when we have an outlier, there's several rules. So first thing we're going to do is plot it, and the reason we're plotting it is to verify, is it really there? We're going to determine if it's an outlier. If so, we have to make sure that the data is accurate. So first thing you always want to do is go back and check your data or your tables, especially when we get into the calculator. We're going to determine if there's a valid reason that the outlier can be removed. So for example, if we go back to our salaries, do we want to tell people that the average salary is $50,000, or do we want to say, you know, our average salary of our individual contributors is $34,000? Because you're probably only have one CFO in there, right? And then the outliers usually result in gaps or clusters, and you have to identify these as unusual characteristics. That's why in the very beginning I said sometimes we have an unusual characteristic. We see that up here. So we would say there's a gap in the data from 90 to 100. So we had no A's, but we had 100 that was right here. Okay? Almost done. So here is a problem, an example of how you're going to see this on the AP test. So what this says is, how do the number of people living in the household in the United Kingdom and South Africa compare? So to answer this question, 50 random households were selected from each country. So 50 from South Africa and 50 from the United Kingdom. So we had all of these 50 households, and they're looking at how many people, how do the numbers of people living in each household compare, okay? So I have the answer down here for you already, so let's talk through this. So if we look at just the shape, we see that this shape right here, I'm just going to do this, that this is going to be skewed right. And I'm going to say that this is pretty symmetric, we don't really have a big tail to the left. We don't really have a tail to the right. We have about the same amount of values. Now, it doesn't mean that it's uniform. What it just means is that it's symmetric, where we have about the same number of values. It doesn't have this long tail. So let's look and see what it says about shape down here. Okay, the distribution of a household size for South Africa is skewed to the right, with a single peak at 4 people, a clear gap between 15 and 26 people. The distribution of a household size for the UK sample is roughly symmetric, with a single peak at 4 people. Okay, so here's what we have. We have this unimodal peak right here. So we have this peak that's here, we have this peak that's here. So we can say that we have a peak at 4, and we also have a peak at 4. Now, what makes this AP worthy is the context of the problem. Include the context. That's what this says down here. And that's what I have. The distribution of a household size for South Africa is. We don't just say South Africa is skewed right and United Kingdom is symmetric. We say the distribution of a household size is. Okay? For outliers, here this says there's a clear gap between 15 and 26 people. I would have probably put this down here under outliers, because this also talks specifically about our gaps and clusters. So what's not important is the order. Like, this is broken out very specifically: shape, outlier, center, and variability. What they're going to be looking for is, did you cover everything that you need to cover? Okay. Outliers. So up here, if I look at my outliers, this is absolutely an outlier. This is maybe an outlier, and I have no outliers here. Now, they're missing something in this distribution, or in this description. So it says, the 2 largest values in the South African dot plot are households with 15 and 26 people, appear to be outliers. What you have to say on this is that they are upper outliers. These are on the upper end of the data. If I had an outlier, let's see, it wouldn't be there, it would be here at 0. If I had an outlier at 0, then I would say it's a lower outlier. So anything over here would be lower, and anything that's up here is going to be an upper outlier. Okay, we talk about the center. The household sizes for South Africa sample, which is about 6 people, tend to be larger than the UK sample, where the median is about 4 people. So 2 takeaways on this. It gives you quantitative data. It gives you a value. And then it uses this key term, larger than. So if we go over here, it says you have to compare these values explicitly using words like greater than, less than, and about the same as. And that's what this says. This is like, if you look at how many people are in each house in South Africa, our median is probably here, versus our median is going to be this big one right here. So the median here at 4 versus 6 in South Africa is larger. Okay? And then variability. Remember, variability is also called spread. So the household sizes for South African sample vary more. Okay, that goes back over here, varies greater. So our low is 3 people and our high is 26 people, versus the United Kingdom, which is, 2 people and 6 people. So household sizes vary more than for the UK. Okay, we're going to do a lot more practice on this over the next couple weeks, but right away I need you to start thinking about that acronym SOX when you talk about these. Okay?